In this video, we are going to be giving a tutorial on how to create a model of reinforced concrete slab using the SAFI GSE concrete application. The SAFI GSE is a leading structural engineering software for the analysis and design of structures for concrete, steel, wood, and aluminum. The software is a great tool to help design and analyze various structures with many automated design functions that still allows any user to personalize any design elements. The SAFI GSE supports the latest design standards for Canadian, American, and international standards for concrete, steel, wood, and aluminum. The procedures presented in this example will apply to any other design standards supported by the program. This example shows all the modeling, analysis, and design steps using the Concrete Slab Design Assistant. This is a model of a simple two-way slab. The columns have a height of 2 meters above and below the slab. The spacing of the columns is 5.5 meters between axes A and B and C and D, and 6 meters between axes B and C. The spacing of the columns between the axes 1 to 5 is 5.5 meters. The border of the slab is extended to 100 millimeters from the face of the exterior supports. Let's start a new file by using the new command from the File menu. Since this is a 3D model, select 3D in the Analysis Mode section in the General Options command from the Tools menu. The first thing to do when creating a new model is to define the grids according to the requirements of the model. Click on the Grid button from the Addition toolbar. We will use this grid for the addition of the geometry. First, change the plane of the grid to obtain a horizontal grid, plane XZ. Next, click on the Edit Lines button in the lines along the axis X section. The main spans will have a spacing of 5,500 millimeters or 6,000 millimeters. We will keep the first 6 lines of this table. We will edit the lines with the absolute coordinates column. The coordinate will be set to -250, 0, 5,500, 11,500, 17,000, and 17,250. The first and last lines will be left blank with no extension at the start, and the end will have no label. The line 2 to 5 will be identified from A to D and press OK. In the same way, we will edit the lines in the other direction. Click on the Edit Lines button in the lines along the Z-axis. From this axis, we will keep the first 7 lines of this table. We will edit the lines with the absolute coordinates column. The coordinate will be set to -250, 0, 5,500, 11,000, 16,500, 22,000, and 22,250. The first and last lines will be left blank with no extension at the start and the end with no label. The line 2 to 6 will be identified from 1 to 5 and we will press OK. We can now press OK on the Grid menu as well. By clicking the Top View button from the Camera toolbar, we can see the grid that we had just created. Notice that the global axes are displayed in the bottom left corner of the screen. The y-axes should now head out of the screen. The y-axis will be our gravity axis for this model. We will now create the different section properties used in this model. First, let's define the plate section used for the slab. In the menu Plate, Section, Plate and Shells, we will define a plate element section. The slab has a thickness of 180 millimeters and is made of a standard 30 MPa concrete. The material used is the predefined 30 MPa concrete in the material library, number 15. In this example, the default parameters for crack deflections will not be used since the reinforcement of the integration lines will be used to complete the cracking of the slab. We will come back to these parameters later. We will now create the column of the member elements definition. To define the column section, select the non-standard section from the table, Section, Non-standard section. Two types of columns are used in this model, and there are also some member elements positioned on the perimeter of the slab to distribute the exterior wall loads. These members are used to distribute the exterior wall loads. The first section is a square section of 300 mm made of 300 MPa concrete. A name must be assigned to this section. The second section is a rectangular section of 300 mm by 600 mm made of 30 MPa concrete. The third section will be placed on the perimeter of the slab to distribute the load caused by the weight of the exterior walls. The section is 100 mm wide and has a thickness as a slab of 180 mm. This section is not intended to have significant resistance to the applied loads. A new material can be created for this section on the right side of the material list. This section will use a material of the generic other type with significantly reduced resistance. The elastic modulus is reduced to 100 MPa. When the grid is properly defined, the geometry may be quickly created. The model may be created in different ways depending on your preferences and work methods. We will simply show you one of the many ways that you can create a model. First, we will create the joints for the base of the model. We will simply select the Add a Joints command and click at every intersection of the labeled axes, from A to D and 1 to 5. You can click at the intersection on the grid, or use the box selection command by maintaining the mouse button pressed. Make sure that the created joints are only at the marked intersection of the columns and that they are not present at any of the slab's border. We will use these joints to create the columns supporting the slab. We will first select all the joints in the model. Then, we will open the Move, Copy, Extrude dialog box from the Addition toolbar. We will use the Extrude command for -2000 mm and click on the Extrude button from this dialog box. We will then do the same thing again, but this time with 2000 mm. We now have half columns extending from the top and the bottom of our slab. We will now set the support properties for the slab. Press the left button of the mouse, make a window around the base joints, and release the mouse button to select the joints at the bottom of the column. When the base joints are selected, the support conditions may be assigned to them. Click on the Joint Attributes button from the Addition toolbar. From the dialog box displayed, specify the support conditions as movement restrained in X, Y, and Z, as well as a rotation restrained in the Y-axes. We can now select the joints at the top of the columns. For these joints, specify the support conditions as movement restrained in X and Z only, as well as rotation restrained in the Y-axes. Make sure the movement in the Y-axes is not selected. A symbol representing the support conditions defined should appear on the selected joints. To quickly select the columns, you may use the Special Selection command from the Edit Selection submenu. In this menu, select the Element Orientation option in the Criterion section, Member in the Entity Type section along the Y-axis, and then click the Select button. All the columns in the model will be selected. With the Member Attributes command, you can attribute the 300 by 600 mm section to the selected members. The majority of the columns supporting the slab will use this section. However, some modifications are required to complete this example. Let's select the columns at the four corners of the slab. Select the column by using the Select by window. Hold the Shift key and add more elements to the selection. With the Member Attributes command, you can attribute the 300 by 300 section to the members. Lastly, the columns of the rows 2, 3, and 4 on the axes A and D are rotated 90 degrees to be aligned with the edge of the slab. Select the columns by using the Select by window and holding the Shift key to select both sides. With the Member Attributes command, you can define the rotation of the section to 90 degrees at the bottom of the menu. We will create a finite element mesh for the floor of our slab using the Mesh Contour tools of the SAFI GSE. To create the slab perimeter, activate the Add command from the Edit Mesh Contour menu, then select Add Perimeter. The order in which the first two perimeter corners are selected will determine the orientation of the local axis of the slab. By tracing the perimeter following A5, F5, F1, A1, and closing the contour back on A5, the mesh contour perimeter local axes will be aligned with the global reference axes. We will set the plate properties to the plate element we previously created and set the plate size to 350 mm. It is strongly recommended to add the refinement areas to represent the area of the support. Even if this step is not necessary, this will help obtaining more accurate finite element results of each support. To create the refinement areas, activate the Add command from the Edit Mesh Contour menu, then select Add Refinements Area. Select the rectangular shape and set the length and width to 500 mm. Set the plate type to be the same as the main mesh contour and the plate size to 250 mm. To place the refinement area, select the main slab perimeter and then click on each intersection of the grid. The same information filled in this dialog box will be kept on the next operation, so you don't need to rewrite them again. Once the refinement areas are placed, select the Generate Mesh button to start the automated generation of the slab mesh. Some members must be placed on the border of the slab to distribute the additional dead load caused by the exterior wall. These members can be placed manually with the Add Member command in the Edit toolbar. Click on the edge corner of each side of the slab to create a continuous member going from end to end of each edge. To quickly select the border members, you may use the Special Selection command from the Edit Selection submenu. Select the Element Orientation option, Members in the Entity Type section, and along XZ, then click on the Select button. The members surrounding the slab will now be selected. Now we will select the Attach Crossing Member in the Section menu with the option Keep Physical Members. This operation will divide each member at each intersection of the plate element, allowing them to transfer the loads to the plates. Once the members are subdivided, their properties can be adjusted for this model. With the Member Attributes command, you can set the Analysis section properties for the exterior members, 100 by 180 mm. These members are not intended to have any structural resistance and will only be used to distribute the loads. Finally, a selection group of these members will be used later for the attribution of the loads caused by the exterior walls. To create a new selection group, open the Edit, Selection, Define Group command. In order to use the automated slab design functionalities, it is necessary to define a slab design group. The definition of this group includes the parameters of the bars, the concrete cover, and the development pattern used in the automated design. We will create one design group for the slab. Select the Reinforced Concrete Slab Design Groups command from the Concrete menu. For this example, 15 to 400 MPa Canadian bars are used with the 22 mm concrete cover for the top and bottom layers. To better fit the design results given in the example, the minimal reinforcement is not activated and the extension of the bars will not be activated. Once the finite elements of the slab are generated, it is possible to generate the design strips with the Slab Design Assistant. To enter the Slab Design Assistant interface, first select the perimeter of the slab, then select the Slab Design Strips Assistant. The generation of the design strips is done in two separate steps: the generation of the column lines and the generation of the design strips in the form of integration lines. Once in the interface, a top view of the slab contour is visible as well as the supports of the slab. The Generate Column Line button is on the top left corner of the interface. The Generate Column Line button is on the top left corner of the interface. A column line is used as a guide for the column strip location. They can be placed on the supports along two principal axes of the slab. The automated column line function allows to automatically detect the column lines in both axes of the slab. Select the Generate Column Line option and click. Some parameters are also adjustable to facilitate the column line generation in a more complex model. It is not necessary to modify these default parameters. We can simply select the OK button to confirm the generation. Even though they are not needed in this example, Several functionalities on the top of the interface also allow the user to easily modify any column strip within the assistant. In this example, the design bands along the horizontal axes X, 2, 3, and 4, and the bands C and D on the vertical axes Y have a set width of 2,750 millimeters. The width of a column band can be manually set by double-clicking on the line and specifying the width to the desired value. If this parameter is set at its default value, the width of the strip will be calculated automatically. Once all the column lines are defined in the model, it is possible to use the automated design strip generation command. This command will automatically generate the integration lines. The integration lines represent the design strips adapted to the geometry of the column lines of the slab. We will select the Generate Design Strip command. The design group previously created will be attributed to the column strip and the middle strip. The design group is set to the one previously defined. This model will use column bands for the automated design. We can click the OK button and launch the generation of the strips. The column strips will be generated following the column lines in each principal directions of the slab. The width of the column strip is computed as the quarter of the shorter of the two spans of a bidirectional bay. The remaining spaces between the column strips will be defined as middle strips. As you can see, the surface of the slab is covered with design strips following the columns in the X and Y axes. We will define the basic loads for this example. The basic loads are families of loads acting on the structure. The different basic load types are typically the dead loads, the live loads, the snow loads, and the wind loads. For this example, we will use the dead loads, additional dead loads, and live loads. Each of the loads will be attributed to their respective load types. All loads added to a given basic load will have the same factor for a given load combination. Note that the new basic loads may be added at any time. We will now define the load combination used for this example. Select the Load Combinations command from the Tables menu. The load combinations for this model are generated using the Load Combination Wizard according to the NBCC 2015 code. Select the combination option for Load Resistance Factor Design, LRFD, and Fatigue and Crack Slab Deflections. Some additional information is required to automatically generate the load combinations needed to evaluate the crack deflection of the slab. The Load Combination Wizard allows to specify which load will be used for the generation of the cracked load cases. Each of these analyses must be done with specific types of loads. The deflections obtained with these 4 analyses will be used to compute the required service limit states. Select Include for the dead load and the additional dead load and assign each load to their respective load type. In this example, only one live load combination is used. To define this load combination, select Include for the live load and set 0.2 for the ratio of sustained load. Select Include for the live load and set 0.2 for the ratio of sustained load. To view all the generated load combinations, click on the Table button in the upper right corner of the dialog box. In order to obtain the results for deflection criterions for a cracked concrete slab, it is necessary to define 4 different load cases. These combinations will be used to evaluate 2 cases of immediate deflections and 2 cases for long-term deflections. The Load Combination Wizard was used for the generation of the load cases with the cracked slab deflection parameter active, hence we have already generated the 4 load cases. These combinations will be of the type cracked, SLS, and named accordingly. This example uses general parameters similar to the default values. We will use some typical construction stage times. The long-term deflection parameter will be set to their default parameter. The pressure loads applied to the floors are a dead load of 4.32 kilonewtons per square meter, an additional dead load of 1.0 kilonewtons per square meter, and a live load of 2.4 kilonewtons per square meter. First, select the slab's mesh contour. Then, click on the Contour Loads command from the Edit Loads menu. We will add all the pressure loads from this Windows menu. Click on the Pressure tab to display the input data for the contour loads and select Dead Load in the basic load list at minus 4.32 kN in the PY direction and click the Add button to assign this load to the selected contour. Now, for the additional dead load, select the additional dead load in the basic load list at minus 1 kN and in the PY direction, click on the Add button. And for the live load, select the live load in the basic load list at minus 2.4 kN in the PY direction and click on the Add button. The pressure load just defined should be visible on the screen. If not, select the toggle load visibility in the View menu on the side of the screen and then select Basic Load. An additional dead load of 4.4 kN will be added to the members on the perimeter of the slab. To define these loads, with the command fetch selection group, recover the selection group containing the exterior members of the slab. To add the additional dead load caused by the exterior walls, select the command members loads from the Assign Loads menu. Select the Uniform Distribution tab and select the additional dead load. Set the value of minus 4.4 kN in the vertical direction FY. As you can see, we have 3 different pressure loads on the slab in blue, as well as the member loads on the perimeter of the slab in red. We will hide the face of the plate in the Display Option menu and lower the display size of the joints to 10%. We will also hide the members on the perimeter of the slab before reviewing the results of the analysis. We are now ready to run the analysis of the structure. The design parameter should be set to the design, reinforced concrete, and the option Calculate Slab Deflections should be selected. We will use the 3 loading steps to compute the crack deflection. Then, click on the Run button. Once the structure is analyzed, we can verify that the results are correct and that they correspond to what we are expecting. The results bar on the right side of the screen can be used to access all the results of the analyses. We can choose one or more load combinations from the Combination button. The first button allows to define the results, which will be shown for the entire structure if the checkbox beside is activated. The second button allows to view the numerical results in tables. The third button allows to view the results by means of charts along with the numerical values. For a better visibility of the internal deformations of the slab plate elements, toggle only the visibility of the cracked D plus SD plus L, dead additional, dead, and live load combinations. Let's start by displaying the internal deformations of the slab. Click on the first button from the Analysis section of the Results toolbar to open the Static Analysis Results dialog box. In this dialog box, check the internal option located in the Deformations. In this dialog box, check the MZ Bending option located in the Forces section and uncheck the Internal Deformations. You should see the internal bending moment along the design strips on the screen corresponding to the first load combination. In the same way, check the FY Shear option located in the Forces section and uncheck the MZ Bending and then click OK. The analysis results can be visualized in further details for each design strip. These results can be visualized either for a specific load combination or for the envelope of all forces. For the integration line, the member convention is used. The MZ, DES, and UNIF bending moment curve can be shown in the integration line slab internal forces. These results are used to determine the uniform distribution of the reinforcements across the width of the strip. In this menu, the shear and displacements are also shown. The integration line, transverse forces, allow to have a detailed overview of the forces on a cross-section of the design strips. Information about the design strips can be found by selecting the command Integration Line Attributes, or shortcut G, and selecting the integration line in the model. The Integration Line information menu is split into two tabs. The General tab shows the different geometrical informations about the integration line. The Slab tab shows the concrete design and the analysis parameter for the design strips. Once the analysis is completed in the Reinforced Concrete Design mode, it is possible to see the reinforcements of each of the slab's design strips. Reinforcements are separated in individual reinforcement groups. Each group is characterized by a bar type and grade, a starting point, and a length. The amount of reinforcement in the strips is represented by the spacings between the centers of each bar. For convenience, the table also prevents the equivalent number of bars for the width of the strip rounded up. Each reinforcement group is selectable and will be highlighted in the 3D representation of the slab strip. Each reinforcement group is editable. This model uses column band design for the longitudinal reinforcement. This option is used to optimize the reinforcement distribution at the peak negative moment at the face of the support. This option allows to have two different spacings of reinforcement bars in a single reinforcement group. It is also possible to visualize the reinforcement of the slab in 2D, and this view prevents the reinforcement group with the bar spacings. Let's now view the results specific for concrete design. Click on the slab bending command from the Reinforced Concrete submenu, and then click on one of the integration lines of the slab. The following dialog box should be displayed, presenting the bending resistant curves for integration lines. The dashed line are the resistance envelope provided by the reinforcement. In the same manner, click on the slab shear command from the Reinforced Concrete submenu, and then click on one of the integration lines of the slab. The dashed lines are the resistance envelope provided by the reinforcement. In the same manner, click on the slab deflection command from the Reinforced Concrete submenu to view the maximum deflection for each of the load cases. The punching shear analysis is directly linked to any joints that have been defined as a slab support of type column in the Joint Properties Concrete tab. By defining the geometrical properties of the slab supporting joint, SAFI concrete analysis will determine the shear perimeter around the support. Support properties can be defined or edited manually or automatically calculated by using the Recalculate Slab Supports function for the associated slab perimeter. Two types of force calculations can be used during the analyses: the sum of the reaction at the joint and the sum of the shear in the plates along the perimeter. The punching shear around the support is visible by clicking on the slab punching shear command. The limit state is displayed at each support for each of the load combinations. The limit state numerical values are displayed on the support perimeter where the most critical value is located. The calculation of the long-term deflection is based on 4 load combinations defined in the cracked elements deflection parameters. Since a nonlinear analysis is necessary to consider the cracking of the concrete slab, each analysis of the immediate cracking is performed separately. The amount of cracking is calculated individually for each plate element. The cracking depends on the reinforcement present in the slab as well as the bending moment applied to the slab. From the Contour command, select the Slab Deflection Results tab to access the cracked reduction factor for both directions. The reduction factor, caused by the cracking of the slab, can be viewed for both main directions of the slab perimeter, X and Y. The reduction factors will vary for each of the cracked SLS load cases. The factors are evaluated individually for each plate according to the bending moments and the amount of reinforcements in each direction. The cracking of the slab will result in a reduction of effective inertia of the slab. This reduction of the inertia will result in an increase of the deflections in the slab. As the load increases, the level of cracking increases, and the deflections increase at a rate greater than the load for most cases. The long-term deflections are obtained by combining the different immediate load cases with their respective time-related factor. It is possible to obtain the immediate deflection caused for an individual types of load by combining the 4 cases analyzed. The long-term deflection command allows to view the long-term slab deflections at any joint of the model. This command shows the deflection caused by each load types over time. Each limit state of the concrete elements can be visualized directly on the model. To display the results of the limit state computations directly on the structure, use the options command from the analysis Concrete Results Reinforced Concrete submenu. In the dialog box, select the type of results you want to see. To display these results, activate the display command just beside the analysis results button. Thank you for watching. Please visit our website at www.safi.com for additional information about our Safi GSE structural products. We hope to see you soon.